Right, now we're going to take a look at section 4.1, which is vector spaces and subspaces. Now, this is going to be looking at some concepts that we've already seen, but we're going to try to describe them a little bit more abstractly. So one of the things we tend to do in mathematics is we take something that we're familiar with or that we understand a little bit, and we try to describe it in as few things as possible. So try to make the description of it as small as possible. And then we take that description and see if it applies to other things. And we take that description and we see if we can find some properties of that without starting from where we were before, but see if we can generalize it some. And that's kind of the idea of some of the things that we're going to be seeing in this chapter. So the first idea is a vector space. So we've seen the idea of vectors and vector spaces. We've seen the idea that a vector is kind of like this standing matrix, an n by 1 matrix, a matrix with a single column. What we're going to do now is, now that we have a bit of an understanding about a vector space, we're going to pull out the properties of it that define it, that describe it, but we're going to stop referring to it as this tower of numbers. We're going to refer to it a little bit more abstractly. So a vector space technically is any group of objects that satisfies these 10 properties. So the 10 properties are all things we're kind of familiar with. So the first one is that you have the idea of addition, that you can add things together and you stay in your group. You never leave your group by adding things together. You can add things together in whatever order you want. You can group things together when you're adding them in whatever way you want. You can group the first two things, or you can group the second and third things before adding the other thing. It doesn't matter what order you group things in. The idea of a zero vector, a zero element, that when you add it to any vector, it comes out the same. We get into the negatives, that there is a negative for every vector. So there's something that you can add, no matter what you start with, there's something else you can add to it to get this zero element. And there's the idea of multiplication, scalar multiplication, that anytime you multiply a vector, anytime you multiply anything in this group by a number, you stay in the group. It has two distributive ideas, saying that if you're multiplying the sum of two items in this group, you could multiply each individually and then add. You get the same result. The second one says that if you're adding two numbers and then multiplying, you could multiply the each number by the vector and then add them. So it doesn't matter what order you do that in. You can distribute your numbers. It has another associative property where if you're multiplying two numbers and then multiplying by a vector, well, you can multiply by the vector first and then multiply again after that. So you can do the scalar multiplication in different order. And it has the idea of a 1, a scalar multiple 1, that there's some scalar that you multiply any vector by it, you end up with the same vector. Now you'll notice we've dealt with vectors an awful lot. You take vectors, a vector space, and remember a vector space being kind of the thing generated by vectors, then it satisfies all of these properties. So nothing in these properties are new. But notice that this definition doesn't have a vector in it the way that we've been thinking about it. It just says any group of things that satisfy these 10 definitions is called a vector space. Whether or not it's an n by 1 matrix or something else, if it satisfies these 10 conditions, it is called a vector space. This is the idea of abstraction. We had a very concrete example of these n by 1 matrices that had these properties. What we do is we abstract it. We take the definition, the things that describe it, and we say, okay, well, maybe it applies to not only these towers of numbers, maybe there's some other groups of things that it applies to. And we're going to see a couple of examples of other groups of things that aren't n by 1 matrices, where these examples apply, or these definitions apply. So some examples, and some of these are things that you'd be very familiar with. Rn. We've talked an awful lot about Rn being the set of all vectors with n elements. That is a vector space. The second example, the zero element, the zero vector. That in itself is a vector space. You think about how it satisfies these 10 definitions. Things like if you take any two elements in your group, add them together, you stay in your group. Well, the only element in there is 0. 0 plus 0 is 0. You don't leave the group by adding things together. Multiplied by any number, what do you get? You get 0. It's still in the group. It's still in that set. The 0 element itself is a vector space. We've seen lots of examples of the span of two vectors, where it's everything you can possibly build out of them by linear combinations. That's a vector space. Now, this last one might be something that you haven't thought about before. When we talk about vectors, when we've talked about vectors up to this point, we've talked about them in the context of being a column, this tower of numbers, an n by 1 matrix. If you look at all of the matrices of a given size, that is also a vector space. Each matrix individually is a vector. You take those 10 definitions, or those 10 properties in that definition, you apply it to the set of all matrices that are 5 by 7, those properties hold. You can add them together. You have the distributive laws. There's a 0 vector in there. What's the 0 vector? It's the 5 by 7 matrix with everything being 0. That is your 0 vector. You have the idea of scalar multiplication. You have all the associative and distributive properties. Every property in there holds for matrices that are 5 by 7. If you look at the entire group as one set, all of those properties hold, and it's not the traditional thing you think about with a vector. So you can see what we've done here. We've taken the idea of a vector, we've explored it, found some of the properties, we've defined it in a slightly different way, and then said, okay, well, let's not think about our elements as being this very strict idea of a vector. What else can they be? Are there other things out there that satisfy all 10 of these properties? Yes, there are. And those matrices is an example of it. But now let's look at an example that's very different. Let n be any number. So say it's the number 4. Let Pn be the set of all polynomials with degree at most n. Now, when I say the set of all polynomials, I'm not talking about getting polynomials and solving them for when they're equal to 0, things like that. I'm saying the polynomials written out. So Pn is all, or P4, for example, is all of the polynomials that have degree at most 4. So things like 3 plus x plus 5x to the 4. You know, things like just x squared by itself. The number 0 is a polynomial of at most degree 4. Negative 1 minus x plus x squared minus 3x to the 4. All of those things, you take every single one of those. That is a vector space. Why is it? Go back to those properties, and you'll see that those properties apply to this set. You take any two polynomials of degree at most 4, add them together, you get a polynomial of degree at most 4. You can add them in whatever order you want. You have the idea that you can multiply them by a number. So 5 times a polynomial is a polynomial of degree at most 4. You have the distributive, the associative properties. They all work for polynomials. You have the 0 the number 0 is a polynomial of degree at most 4, so that satisfies that property of the definition. That set, P4, or Pn, whatever n you want n to be, That is a vector space. So when you're talking about this set P4, the vectors are a single polynomial. Every single polynomial is a vector. So you can see now this is taking the idea of a vector space, and we're no longer applying it to towers of numbers. We're applying it to something else, but it satisfies all of those definitions. The reality is in this course, we are going to be dealing with the familiar column of numbers as our vectors, but a vector space itself is something broader than that. It's a more general idea. And this is something we do often in mathematics. We take something concrete, something we're familiar with, we abstract it, come up with definitions, properties of it that don't specifically refer to the form of what we had, but to the underlying ideas behind it. And then we take those ideas and we see what we can do with them. We see what else they apply to, and we see if we can draw more conclusions out of those ideas that maybe we wouldn't have seen by dealing with our original construct. So this abstraction of a vector space is a very good example of a mathematical process. We also have the idea of a subspace. Now, a subspace is just a vector space itself, but it's one that lives inside a bigger space. So we've already seen a bit of this idea. So a vector space, if you have a vector space and you have some group inside it that is itself a vector space and has three additional properties. It has a property that that smaller group has the zero vector. It has the property that if you take any two items in that smaller group and add them together, you're still in that smaller group. In other words, it's closed under addition. And you have the idea that anything in that smaller group, if you multiply it by any number at all, you stay in the smaller group. You don't leave that the smaller group. You don't go back to the bigger group. That is called closed under scalar multiplication. That is the idea of a subspace. It's a vector space that lives inside another vector space. So a couple of examples. The first one is the type of thing that we've seen before when we talked about subspaces. So if you look at R4, but then you narrow your focus to just look at the elements of R4 where the last two entries in your vector are 0. That is a subspace. Take any of those two, add them together, you're still in that set. The 0 vector is in there, where S1 and S2 is equal to 0, that's in there. And if you multiply anything in S by a number, you're still in S. You still have those bottom two elements being 0. That is an example of a subspace. Now we saw another example of a vector space being the set of all polynomials of degree at most n. Well, here is another example. P3 is a vector space. It is a subspace of P7. Just the polynomials of degree at most 3, that is a subspace of the group of polynomials of degree at most 7. It satisfies all those properties. So it's the idea of a subspace. That leads to our first theorem, that if you have a vector space, any vector space at all, whether it's your polynomials, your matrix, a tower of numbers, anything else that satisfies those 10 conditions, pull out some elements, any number of elements. So these are just individual vectors in your vector space. And then look at the span of them. That is going to be a subspace. So this is a common way of building a subspace. You pick a few elements out, you look at all of the possible linear combinations. That is a subspace. And this, just to clarify, should be everything V1 to Vp, so the span of that entire set. So here's an example where we're going to use that theorem. Look at this. S is this set. So S says that you pick any numbers, A, B, and C, any three numbers, build a four-dimensional vector this way, and look at all the sets of all possible vectors you can build this way using all possible numbers for A, B, and C. Is this a subspace of R4? Well, you see it is contained in R4 because it is a tower of four numbers, but is it a subspace? Does it satisfy those conditions for a subspace? So this is something similar to what we've seen before, and we're going to break this up into its component parts. We can rewrite S as saying that S is the set of all vectors that are linear combinations of some other vectors in this way. It's A times 2, 0, 3, 1, plus B times, take out all the B elements, we get 0, 1, 0, 1, plus C times negative 1, 1, 0, 1, where A, B, and C are any real numbers. So this is giving us another way of describing this, this set S. We've just broken it up into its components. But now we've seen stuff like this before. This is the set of all linear combinations of those three vectors, so it's equal to the span of those three vectors. Oh, that should be, there's an error there. That should be 0, 1, 1, 1. And the third vector is negative 1, 1, 0, 1. So it's the span of those three vectors. By theorem 1, well, S is now exactly equal to the span of three vectors from R4. S is a subspace of R4. Okay, so that's the end of section 4.1. This was a fairly short section and didn't really introduce too many new ideas, but it introduced a new concept, the idea of abstraction, the idea that we are taking a concept that we're familiar with, that in this case, that of vectors, we're boiling it down to its definition and then saying, does that definition apply elsewhere? And are there other things we can do with that definition when we aren't confined to this tower of numbers? So the idea of abstraction was the main concept, the main idea out of this section.